All right, welcome back to the last week of Introduction to Computer Networks. And we have 3 hours of lectures this week. Today, Wednesday, we're going to go through 3 of the quizzes. So this is actually a series of quizzes to try to make sure that you understand why bad news travels slow in distance vector routing. Okay. Tomorrow there will be 4 quizzes. It's again a series of quizzes related to a routing policy in a routing protocol that is very, very important running on the internet called BGP. Okay, so let's go ahead and start the lecture today. Oh, and by the way, the last week, so I keep saying that this is the last week, because the last week, which is next week, there's not going to be lectures on Wednesday, and Thursday is going to be the last exam, exam 3. So no lecture on Wednesday. Make sure that you use the time to review for exam 3, right? And let me emphasize, exam 3, it's going to be the regular length, okay? Regular length. So I know I can trust you guys. Good, so let's not wait and talk about the first topic today. Distance vector. There's actually a major issue in distance vector when the link cost or a node goes away or a node is being added. Then you need to update. When we need to update, when the update is going towards a better direction, for example, lowering the cost, then it spreads out really fast. But if the update is that the link cost is suddenly from something low to something high, that is a bad news, and these bad news will travel slow. Okay, so this sequence of quizzes are here to demonstrate, to show you why it's slow. And so you'll be using distance vector routing following the Bellman-4 equation. You just calculate based on the Bellman-4 equation and the distance vector algorithm. You will see the bad news travels slow. All right. So, okay, let's go on and start with the first quiz. So there's not much lecturing here because I'm just going to give you an example, but the example is going to be lengthy because it's a bad news traveling slow. Okay, so we'll show how slow it is. Okay. Oh, hi. Oh, good. You guys are not late because Polly does have the certain obsession with time because she does find that time is the scarcest resource in the world, okay, in this universe. So Polly oftentimes starts a little bit early because the beginning of this is very straightforward. You can always come back to the video and just quickly go through it. Then you know what needs to be, what you need to pay attention to, okay. And so this topic, bad news travels slow, is going to be just a sequence of quizzes, all right? And so you see here, Polly is going to derive X's distance vector table right after the change. What is the change? It's the same topology that you guys have followed last week, okay? Very simple, 3 nodes, 3 links. And this link here between X and Y was originally costing 4 units. But now it's suddenly changing to 60, which is really, really bad. Okay. And Polly is going to derive X's table. Okay, so this guy's table. So to give you an example and also to help you recollect how Bellman-4 equation works. And then quiz 44 is asking you to do this. You then will derive Y's table, so it's the other guy, the other end of the link, okay, right after the change. And we call that time point T0, okay, good. So to be a little bit more concrete, what we're gonna do is that Polly is gonna derive table for no X, and you will work on the table for Y, all right? And so Polly has already prepared the derivation as a video. Okay, so here's how Polly would derive the table in no X.
Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that would be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy coming, came from no y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz, yeah, to y. So dz to y. And that is in, yeah, distance vector of z came from no z earlier. Z to y, yeah, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, yeah, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
All right, so now your turn. Okay, so work on the table for no y. And you have only 5 minutes. Okay. Yeah, so I see you guys coming up with slightly different solutions. Very interesting. Okay, now, oh, there's a question from Zijun. Are XYZ's table calculated simultaneously or sequentially? Zijun, that is a very, very key question. You know what? In this series of quizzes, they are calculated simultaneously. So they're kind of asynchronous, independently, but asynchronous in a way that when the link change from 4 to 60, X and Y simultaneously detect the change and simultaneously want to change the table. All right. Okay, so that is in a way saying that, hey, that new vector that X just computed, it's actually not there yet in Y's table, okay, before Y tries to compute a new dy. All right, and I think that is why you guys come up with different solutions. So in a way, when you're calculating for node Y detects the change at the same time, and Y wants to recalculate at the same time. So Y here did not receive dx from node X yet. So 0, 50, 150 is not yet in node Y. Okay, so don't worry, let me show you the video how to derive Y's table at T0.
dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cost is link cost yx is 60, link cost yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6, 6 wings. Okay, and that is actually going through no z. So y is going to pick, okay, saying to go to x. Let me send it to z first. And then z says, I know a way to x, which is, yeah, the O impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
All right, so I think some of you are, oh, is that so? Yeah, so there's like, the asynchrony of the messages is also that there's a change up there, but I don't know quite just yet. And so, but I need to update the table, but I don't have full picture. All right, good. Now, quiz 45 then, let's go on. Let's go on. We just finished updating x's table and y's table. So obviously what y perceived the best route is wrong as we see the global topology. So obviously you can imagine that the route computation of distance vector is not very close to converge to the final state yet. So quiz 45 is asking now, try, because x has updated the vector, y also updated the vector. X and y then will what? Forward their vector. And z being x and y's neighbor will receive both of these vectors. So quiz 45 asks you to come up with the new dz after receiving the new dx and the new dy. All right, for this quiz you get 7 minutes. All right, so let's go on and work on it. let's see. So the answer this time seemed consistent. I guess you guys finally see how the nodes are sending messages, and before making decisions, if the messages have not, the updates have not yet arrived, then you need to stick with the old information. Yeah, good. Youxiang, that's a very good question. I'll come back to answer your question right after the video deriving table of z at t1.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. Right? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-4 equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Okay. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finished calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay.
All right, so you guessed. Quiz 46 is then to calculate dy at time t2. All right, so I meant go on and calculate. Yeah, so that 2 question marks. And before you start, let me answer Youxiang's question. That's a very important clarifying question. I think some of you might be confused. How come, right? The initial table looks like, hey, they are already converged. By the way, this topology, how to build and find the final tables that's after all the routes converge to the shortest path, that was already done in quiz 43. So what I'm doing here for quiz 44, 45, and 46 is I assume the network has already converged to the shortest path, and so that first column's table are actually the table X, Y, and Z routers now currently hold before the link update. Okay, so therefore you see the tables are all the same, yeah, because they all converge to the shortest path. So this is not quite the case where we have a topology, okay, and the nodes kind of independently trying to start. And so therefore, there's like an initialization time period that they come up with their own vector. And the other, so for example, in node X, in initialization stage of DV routing, dy and dz will all be what? Infinite, 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 no information. And dx will then only look at the links and the nodes that are next to them. Next to node X. Okay, so this is to clarify that for quiz 44, 45, and 46, I assume that we have already finished computing the shortest path. Okay, and this is the steady state table. But suddenly there's a link cost change. Then the nodes next to the link cost that's changing will start updating. And these updates would trigger the other nodes thinking, nothing's going on, but suddenly receiving a distance vector, and they also need to update. Okay, good. That should address Youxiang's question. And then Kevin was asking the cost. Yes, the cost is for both directions. And Kevin was curious about the packets that might stuck in the loop. Yeah, they will get stuck there until there's finally a route. And if you recall in IPv4, there's a field in the packet header called the time to live, TTL, time to live. In case that packet gets stuck in the loop for 63 hops, then that packet will get dropped. And that is assuming that the packet is sent with the TTL value initialized to 63. Okay. Will arrive destination after the table is fully updated before it is. Yeah. So hey, I just explained. Good. So hey, for quiz 46, you have only 3 minutes now. Okay, sorry for the time pressure. 3 minutes, but that's because I think you guys know how to calculate the table for node y at T2. Okay, 3 minutes. Yeah, so based on what you have typed up, I think you guys have got the hang of how to do the distance vector calculation, right? It is quite straightforward. It's just the Bellman-4 equation. But you see that it can also be a little bit tricky because the computation needs to be strictly based on what the router knows within itself. Okay, we as human beings oftentimes see the topology and we know a lot better. But those routers, the distance vector routers, actually don't know better. They need to stick with what they have. All right. So this last video, and hey, you guys probably see like a trend, right? Oh, the link cost from 6 to 7 and then 8. Guess what would be Z's table like at T3? Yeah, I know you guys are probably, hey, it's probably 9, isn't it? You know what? It is. And if you keep counting, you see that it would take 44 iterations to get the table to converge to the best routes, okay, after the link update. And here's the video to walk through everything so that bad news travels slow and it takes 44 iterations to converge back is clear.
Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x, through neighbor x, neighbor z. Link cost 60, link cost 1, link cost 60, link cost 1. The xx, 0, the zx, look up the table, z's x, 7, 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here, actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only 7 dollars to go to x. And this is going to go on, in fact, because y here is going to announce dy also, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration, okay? And including the initial iteration, that will be what? 44 iteration, okay? Until, z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
All right, so that was bad news, travel slow. So you don't want bad news on distance vector routing. And you see, bad news travel slow, this issue is not like entirely unsolvable. There's actually a solution called poisoned reverse. Okay, here's the idea of poisoned reverse first.
The problem here is, right after link cost change, when y is trying to recompute, the best route to x to z, particularly to x, Bellman-Ford algorithm says y needs to try, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, just to get from y to x. So together, total cost 60. Not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. So y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So z is going to send the packet back to y. And y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, until y discover, the real shortest path to x. So z here, being still under the impression that the best route is the one before the link change, needs to know about the link change. Poison reverse is working this way. This is to help, preventing bad news travel slow. In poison reverse, y and x, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, all your shortest path routes to the other node along the link needs to be changed to infinite. That way it prevents y selecting z as the shortest distance to x.
All right, so there's a very good question from the students. What if in the middle of we trying to iterate and converge for bad news, there's yet another change on the link? Ouch. You know what? If it's changing for a better cause, I think it would actually help speed up and suppress the bad news. All right. But if that change is even worse than the bad news earlier, I think it will just, in the end, the time it takes to converge will be bounded to how long it will take, how many iterations it will take for the second bad news. Okay? But hey, I have to work it through in order to be sure. But on top of my head, I think that's gonna happen. Okay. All right, and you know what? That was the idea of poison reverse. The two nodes next to the link that are changing. Query, ask their neighbors and see if there are paths that go through that link that's changing. Okay, if they do, override the neighbor's table. All right, so let's go through an example just to make sure that it's clear.
Let's use the same example to illustrate how poison reverse works. So taking one step back before we have the link cost change. Node Z here will discover a shortest path to X this way, Z, Y, X. So shortest distance from Z to X is 5, and the next hop router is Y. Now, link XY here, the cost changes from 4 to 16. X, Y, these two routers being connected to the link will be able to discover the link cost change, but Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay? A funny value for the shortest distance from Y to X, which we see from the network after link cost change. There's no way this is the right value. So to avoid having confusion such as this, we should stop. Z from keep telling Y this is the shortest distance. So Z tells Y instead, the distance to X is not 5, instead being infinite. And that is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. If this node here discover there's a route coming from the neighbor and using itself as the next hop. So if Y here discover in one of the neighbor, and this neighbor is using itself as the next hop to a destination. Set this entry here in Y's table to infinite. With now the Zx being changed to infinite, the way we calculate the Y in iteration T0 will be different. So dyx particularly is the entry with different value. It was previously 6. But now let's see how it's going to look like. From Y to X, there are two possible neighbors, X and Z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor X to destination X, dxx. From second neighbor Z to the destination X, dzx. dxx, dzx. Set up table, xx 0, zx infinite. So 0 here, infinite here. Comparing the two, 60 better. Therefore, shortest distance from Y to X is now, the direct link XY. And then, the next point in time in T1, Z here is going to receive the distance vector from X and Y, and this time the YX is 60. That's going to change, the result of the DZX, this entry here. So let's see, DZX. from z to x through two neighbors, link cost being 50 and 1, 50 and 1. The xx and the yx, so xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes, 60 and 1 are the link cost. The xx, 0, the zx, zx, entry value being 50. So 51 compared to 60, 51 wings. So to go from y to x, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so that is the power of doing Poisson reverse. All right, there are 2 more questions. Kevin was asking the link cost, whether it's really asymmetric or, whether the link cost is asymmetric in real world. You know what, in most part of the internet, as far as I know, they are the same. In fact, the cost is always 1. Because delay, more or less similar. Load, you don't want to use traffic load as a metric. So most of the time when they're calculating for the shortest path, they just count number of hops, okay, number of routers in between the source and destination. Because eventually you will find that the buffering time is the thing that's taking the most time. And the more routers there are along the path, the chance of you need to have the packets buffered, delayed, is also higher. Wei San was asking, okay, if that link cost between x and y goes infinity, if the connection is broken, you count, right? You keep counting until infinity. So that is the case that, the network will not work, and there's going to be loops here, there. And that is also the very well-known count to infinity problem in distance vector routing. And some of you might be keen, because how human propagate information is very much like distance vector. Therefore, this distance vector routing is also called or nicknamed rumor network. Very, very interesting, all right? So that actually concludes distance vector, all right? So this very last video is just to do a complete comparison between the link state and distance vector.
Now with both routing algorithms introduced, let's compare the 2 algorithms. LS here stands for link state. DV is the distance vector. Let's compare the message complexity first. If you recall, in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links. Okay, there are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost NE. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. Okay, so overall, the cost can go as high as N cubed. So link state message complexity, not good at all. Distance vector, on the other hand, okay, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, DV is slightly better. Now, the second metric, the speed of convergence. the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being n squared. There's some optimizations one can apply that takes you to n log n time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time, is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase that router is malfunctioning, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DB and then pass the incorrect information further. Each node's table is going to be used by the other. Each node's distance vector is going to be used by others. This error is going to propagate out throughout the network, and it might take a long time for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, link state here is still winning by a head, by a neck.
All right, so that is all for the routing algorithms, all right? Hey, some of you are probably expecting that we discuss also the space complexity of the 2 routing algorithms, but it's not on the slide. You know what? It's on Slack. The Ask Us Anything channel, because in the end of the lecture last week, we kind of started discussing, right, how much memory space is required to keep the distance vector table. Versus for link state routing, we need to track the topology. All right, so we have everything, and there's a question from Kevin. Essentially, I think so the question is very interesting. What if XY is updating the link XY, and then XZ is also updating like link XZ? How would these updates interplay with each other? I think it's a little bit similar to the question earlier that if you started iterating the route changes, if it's a better news, then it would actually help converging faster. If it's even worse news, then it will take longer time. I think that will still be the case. But your question here, Kevin, I am less sure. Because both of the links can be changing for worse. So actually, I'm not quite sure. where how the convergence time will be bounded to, right? I think it's probably how much worse the link update is. Okay, the one that's worse than the other in terms of the link cost change will dominate and decide how long it takes for the network to converge. But hey, again, this is a scenario Polly has not yet thought about. So maybe I'll think a little bit more about it and let you know. All right. Kevin asks, route A, route B are the same. How router decides which route to send the... Oh, okay. That's a very good question, Kevin. If this is a link state, I think there's usually a tiebreaker in the diextra. In distance vector, I think there's also some sort of a tiebreaker that, let me think. In distance vector, right? If two neighbors give you the same cost, right? Which one do you think, do you take? I think, again, a certain tiebreaker there. Maybe the node with the lower ID. All right, good. All right, with that said, that's the end of the lecture today. Sorry for taking more time than usual. Because tomorrow we also have a very full schedule. All right, so looking forward to seeing you tomorrow morning, and go catch the next lecture. Okay, bye. Okay, Kevin, give me a second. Let me end the stream first.